Our lecture today is about linear equations, how to solve simultaneous linear equations. And as I mentioned at the first lecture, I will try my best to give some examples from electrical computer engineering so that you can relate this course. Even when we talk about some certain numerical problems, I don't want this course to be converted in your mind to something that is theoretical, not practical. So we will talk about some practical numerical problems that you might encounter when you solve your system, but we'll see how this can be implemented in circuit. So in this part of the course, or this set of notes, I will concentrate on circuit. I found a lot of applications between the numerical method and circuit. But to start with, which circuit we are talking about here? We are talking about linear circuit, okay? Because there is linear and non-linear circuit. Whatever you studied so far, you studied linear circuit, meaning that the relation between the voltage and the current of the resistance is a straight line. The relation between the flux and the current is a straight line. In the inductor, the relation between the voltage and the charge is a straight line in the capacitor. So this is a linear circuit. This is what we used to do. Every element is linear. However, in real life, these elements are not linear, or they are linear at certain conditions. For example, the inductor. This is the blue line is a straight line of the inductor, and this is assume it's a linear. However, the inductor looks like this. This is how the red line, this is the relation of the inductor. So yes, there is certain part of the inductor is linear, but then after that, going this way or that way, the inductor become a non-linear. Okay, but in this part of you did not study the non-linear inductor, I believe. I don't think you will even study it. Maybe later on at some later stages you might work with the inductor as a nonlinear element. Okay, but in the second set of notes, second set of notes, we'll talk about nonlinear equations, and then we'll see some nonlinear application. Another application is the resistance. The resistance, we assume it's a constant value when it comes to frequency. However, that's not true. For a very high value of frequency, and those who will be studying RF in details later on, you will understand this. Why this is the problem, and why the resistance increase as we increase the frequency. This is the frequency of the signal. If you have a wire, a piece of wire like this, this is a cross-sectional area A with a length L and a conductivity sigma. So your R is your length L divided by sigma times A. Okay, so this is how to find the resistance. Now, if you have very, very high frequency, you have something called the skin effect. What is the skin effect? It means that the current will concentrate in the outer layer of the conductor only. Most of the current will be here, no current will be there. Okay, so the effective cross-sectional area will be smaller, and this will lead that the resistance will increase. This is why you will see the word waveguide if you work with RF signals. Waveguides is basically the cross-sectional area of them, something like this. This is a waveguide. It's not a conductor here. This is a hollow. There is nothing here, no material. Why? Because at this high frequency, the current will only concentrate here. There's nothing in the middle, so you save the material and you have this as air. There's nothing there. Okay. Now, this is linear versus nonlinear circuit. Both does exist, but depending on the conditions. In circuit one that you studied, we always assume that we are working in the linear region. Okay. So we'll start with something based on the poll I did. I think most of you they know Gaussian elimination, but it seems that partial pivoting you never heard of it. Okay, for the LU factorization, I decided not to include it because it is more of linear algebra. So I thought I will just cover Gaussian elimination from different aspects and leave the LU. Maybe if you take a course in linear algebra later on, you will study this. Now for the Gaussian elimination, what we are trying to solve, I'm trying to solve this system of equation. A times X is equal to B. A is a matrix n by n. X is my unknown, n times 1. This is x1, x2, x3, which could be voltages, could be currents, could be anything. And this is equal to my n by 1, which is the output vector. Okay, so this is the system of equations I'm trying to solve. Application of Gaussian eliminations has two steps. First, I use forward elimination, and then I will use back substitution. So what is forward elimination? If I have this set of equations, it's a 4x4 system. So I have 1, 2, 3, 4 unknowns. Okay, so I will take them from the equation format into the matrix format. So this is matrix A, this is X, and this is B. So the coefficients of your variables or unknowns is your matrix A. The output of the equations is matrix or vector B, and vector X is nothing but the set of unknowns. Now the objective is to go from this to this. Let me see if I can take this out. Take this out. Take it out. So as you can see better. I'm not sure how to do that. Press hide. Let me see. Task manager. Oh. Okay, let me check here. Someone is giving me some hints. Let me see here. Taskbar setting. Taskbar setting. Okay. Okay. I think now it's gone. Okay. So basically that's what I want to achieve. What I want to achieve, I want to do a certain elimination. We call them the forward elimination. And by doing this, we will come up with this. Okay. So we will have like sort of a triangle like this. And then we will apply the back substitution. Okay, what do we mean by back substitution? We start with the last equation and find x4, because this is one equation with only one unknown. Find x4, then move up, and here I have two unknowns, x3 and x4. I already know x4, so I can find x3 and so on. So with this, I will be able to find all the variables. So we start with forward elimination, and then we come to find the values. We go for the back substitution. Okay, so let's see this, how we will do this. So we'll start with this set of equations. Okay, a11 x1 plus a12 x2 until xn. So we have an n number of variables, and as you know, if I have an n number of variables, I have to have an n number of equations. Now to do the forward elimination, I need to do an n-1 steps of forward elimination. So I will go from second equation to the end. So I need to do only n-1 eliminations. The first equation, it stays as it is. There will be no elimination at all for the first equation. So how to do that? So what I want to do here, I want to get these values of x1. So I want to keep only x1. Remember, this is the format I have. So x1 does exist only in the first equation. x2 does exist in the two equations, x3 in three equations, etc. So here I want to get rid of everything here. So how to do that? Let's say I want to get rid of this. As you know, in linear algebra, I can add, subtract the equations together without affecting anything. Okay, so I can add two equations. I will get a third equation, which is it just doesn't add any new information. It is just a combination of the other two equations. I can subtract them, and I'm not changing anything. So if I multiply this equation with A21 divided by A11, the whole equation, and then subtract this equation from this equation, A11, then I will get rid when it comes to this equation. So I will subtract this from this, so this will be gone, and so on and so forth. So let's see here. So I will multiply the first equation with this constant, and then I will subtract this minus this. Once I do that, then I will get rid of all the variables. Okay, so when I subtract these two equations from each other, then I will get rid of the all the x1 from the first equation. Then I will do the same thing for the second equation, for the third equation, for the fourth equation, until I have this. I can see here all these equations have no x1, no x1. x1 has been completely removed. Okay, so I need to do that in -1. Then now I need to get rid of x2. x2 now I want to get rid from the third equation. So I will come here, and these two I will get. So I will multiply this by A32 dash divided by A22 dash, multiply this equation, and then subtract. Then I will get rid of this, and so on and so forth. Okay, so now I get rid of all the x2s, and now I will go for, this is the second step, I will go for x3 until I reach to this. So, and this is the end, and now I am set to start my back substitution algorithm. I'm done with the forward elimination, and now I am ready to do the back substitution. I will start from here. I will start by finding the last variable, which is xn, bn n minus 1 divided by a n minus 1. And then once I know xn, I will go and find xn minus 1, which is the equation just on top of it. And because now I will have two variables, but one of them is known to me, so I can find xn minus 1, etc. I can put this into a matrix format, or into summation, in a summation format. So x at any I equal to the pi of that minus all of these variables that are coming from the previous steps, and I can put it in a summation like this. Don't get offended by the equation. It looks ugly, but it's very, very simple. And if we apply it here in this example, then you will understand. Okay, so let's find this. It says find the parabola of y equal to a plus bx plus cx squared that passes through the following points. We have 1, 2, 3 points. So I will generate 3 equations, and then from these 3 equations, I need to find these variables. So in the first equation, this is your x1, y1, x2, y2, x3, y3. So the parabola is going through all these 3 points, so it satisfies this equation. So coming here, the first equation, here I want to generate the equations because I don't have them yet. So here y, which is 1, equal to a plus bx, x is 1, plus cx squared plus c. So this is the first equation. The second equation, y is minus 1 is equal to a plus bx is 2, so 2b, plus cx squared, so it is 4c. The last equation is y is 1 equal to a plus bx, which is 3b plus 9c. So this is the 3 equations I want to solve. And these 3 equations are having 3 unknowns. I need to put them in the right format. So the right format is 1, 1, 1, 1, 2, 4, 1, 3, 9, and then 1, minus 1, and 1. So this is the system of equation. This is how we write them. And then we are ready to start solving these equations. So this is my A matrix, and this is my B vector. So we put them augmented together in one big matrix, and we will start to apply the algorithm. Okay, so first we start with the forward elimination. So let me remind you of the matrix. This is my matrix. I want to deal with it. 1, 1, 1, 1, 2, 3, 1, 4, 9, 1, minus 1, and 1. Okay. So now I want to get rid of this one. The first thing, how to do that? Now, since these are the same order, I don't need to multiply by any factor. So just subtract. Now my row 2, the new one, will become equal to row 2 minus row 1. I will just subtract these two rows together. So we right now have the matrix here. Of course, I don't touch the first line, so it is 1, 1, 1, 1. Okay. Now when I subtract this minus this, this is 0. 2 minus 1 is 1. 4 minus 1 is 3. Minus 1 is minus 2. And then I will do what is my row 3. It will be, again, I don't need to do anything, so I'll just subtract row 3 minus row 1. Always you subtract from row 1. So 1 minus 1 is 0. 3 minus 1 is 2. 9 minus 1 is 8. And this is 0. So now I finished the first step. Now here I have a number of rows is 3. I need 2 steps. So the first step, I need to get rid of the all the other variables here in the n-1 equation. And then I will go and get rid of this. Then I am set. So I need 2 steps. The first step is to get rid of the variables in the first column, and then the second column, and that's it. Okay. So now I need to do this. So now this is this job is done. I don't touch it anymore. So now it's between these two. So it's obviously that I need to subtract this from 2 times this to get rid of the 2. So now my matrix will be 1, 1, 1. This is, I don't touch it now. And now the second row, I don't touch it as well. I keep it as it is, minus 2. And now my row 3 will equal to my row 3 minus 2 times row 2. So I multiply row 2 by 2 and subtract this. So this is 0. 2 minus 2 is 0. 8 minus 6 is 2. 0 minus 2 times minus 2, which is 4. Now I have the matrix in the format I am really interested in. So now I'm ready to find the variables. I'm ready to find my unknowns. Okay, so now my matrix is in that format. This is the last thing I have, which is 1, 1, 1, 1, 0, 1, 3, minus 2, 0, 0, 2, and 4. So I'm done with the first step, which is the forward elimination. It's a forward going from up, down. Now I will go for the backward substitution, which is, so start from here, from the last equation. So I have here, this is nothing but, remember, this equation actually is this equation. This is actually the equation, how it looks like. I just augmented in this format, but the equation is actually look like this. I just take out the variable. This is the equation, how it look like. So there's A, B, C. I just take them out to make it easier to deal with. Okay, so I augment the input matrix A, the output vector B in one matrix, but this is how it looks like. So in C here, you will have 2C is equal to actually to 4 from the last equation. So from this, you can C is equal to 2. Now I can go upward. Okay, so backward substitution, you go from the last line and you go up. So you have here B plus 3C is equal to minus 2. So your B is equal to minus 2 minus 3C, but C is equal to 2, so B is equal to minus 8. Now you go to the last equation, which is A plus B plus C is equal to 1. So your A is equal to 1 minus B minus C is equal to 1 minus 8 minus C, which is 2, and this is equal to 7. So now I found everything. So the equation I'm looking for is equal to 7 minus 8x plus 2x squared. This is your A, your B, and your C. So with this, I'm done with finding the equations. Okay. Any question? Anything not clear here? Let me see here if there is. Okay, if there's any question. It seems that what I've ever mentioned here is something that you already know. And this is from the feedback I received in the survey. So let's move on. Okay. Now, the question here says, why don't we apply the matrix multiplication to A, B, C? I don't understand the question. What do you mean by apply the matrix multiplication? Do you mean that finding the inverse of the matrix? If I understand you correctly, maybe you want to solve the equation as such. It is AX equal to B. So you want to find B. How to find, sorry, X is equal to A inverse times B. This is what you meant? There are other techniques, yeah, okay. There are some other techniques. This is just one of them, and that's not the focus of this course. The focus of the course is to use the iterative methods, which will be covered later on. This is just to go through one of the techniques. There are some other techniques for the, solving linear equations. As I said, there is the LU, the LUM. There are many other techniques, but I am not really interested to go through linear algebra here. I am more interested into just going through some of the techniques. We'll know how we will be able to program them, and then we will compare this with the iterative techniques. So, but the focus here is the iterative techniques, not the Gauss elimination or the modified Gauss elimination. The entire row including the B row, so we multiply the row in X. I did multiply. This is here the equations. When I go back here, if I could understand you correctly, here I just multiply the row with this. So this is becomes multiplying the row with the column. Okay, I'm not sure if still I got you or not. Maybe after this you can even talk to me or something to understand your question better. Okay, so let's see what are the drawbacks of the Gauss eliminations. They are not perfect. Okay, so if I want to solve this, let's start with the first one. If I want to solve this system of equations, okay, so I will write them here in the matrix form: 12, 10, minus 7, 6, 5, 3, and 24 minus 1 and 5, okay, 15, 14, 28. Now, one thing you have to know that I want to apply a computer programming to the algorithm. I don't want to do it by hand. because okay, 3 by 3 system, yes, I can do it by hand. But if I have 1,000 by 1,000 systems, I don't want to do that by hand. I want to program the computer. So this algorithm, because it is systematic, I can program it and I can apply it. So the computer will do this automatically. Okay, so put this in mind and see what will happen here. So I want to apply here. So I need to multiply this by 0.5 and subtract. So here the equations will be equal to 12, 10 minus 7, 15. Okay, so I will multiply this, the first row. So the row 2 will be row 2 minus 1/2 row 1. Okay, so this 6 minus 0, 6, 0, 5 minus 5, 0, and then we will have this is 6.5 and 6.5. Now for row 3, I will multiply this by 2 and then I subtract. Okay, so it becomes row 3 minus 2 row 1, so becomes 0 minus 21, 19 and minus 2. Now I want to come here and do the same thing. Okay, I want to eliminate this. Wait a second, this is a 0. So as we know, what is the algorithm? We just multiply. I need to multiply this to get rid of the 0 by minus 21 over 0. This is what we do every time. To eliminate this, I multiply 6 divided by 12, which is half. I multiply 24 divided by 12, which is 2. Now I need to multiply minus 21 divided by 0, and this is, as you know, is undefined. Okay, so this is a problem. Now, someone may say, "Oh, but okay, we can notice this. We can do something about it." No, you don't notice this because this is a programmed algorithm. The algorithm will not check if there's 0 or not 0. The algorithm will just do that automatically, and then they will stuck with this. So this is the first problem with the Gauss elimination, that sometimes you might end up dividing by 0. Now, the second problem is the round off error. Remember, we have a round off error problem, but in Gauss elimination, this problem can be huge. The impact of it can be huge, as we'll see here. So if I want to use fraction, not decimals, meaning I'm working with what we call the exact solution. What do we mean by that? For example, if I have 2 over 3, it is 2 over 3. It's not 0.6667 or 666. Depends. Do you want to go for round off or elimination of the last digit? Sometimes you round off the last digit, depends on how many significant digits you want to go for, or you just truncate it by truncation. You eliminate it. Okay. So in hand calculation, I can keep it like this, and we will see this. And in the homework, I ask you to do this, to notice this. If I go for exact solution, means I keep the fraction as this. I don't need to do any round off using the decimal. The round off is only for the decimals. Okay. So if I do that, this is the solution. 1, 1, 1. Okay. Now, if I solve this on a computer using 5 significant digits, which is not bad, using 5 significant digits, this is the answer I will get. And please try this. Try to do this as an exercise. So you'll see that the first one is 0.625, but the answer is actually 1. So you see how big is the difference. It's a huge difference between this and this. X2, 1.5, it is like 33% error. Only X3 is very, very close. This is the only thing. If I go by 6 significant digits, I get much better results, but still, I am off by some good error here. Sometimes 1.05 is really a huge error. Depends on my application. So this is another issue with using the Gauss elimination. So how to avoid these two drawbacks? For the significant digits, okay, instead of 6, use 8, use 9, use 10, okay? So this is will decrease the amount of error. However, it does not avoid dividing by 0. Dividing by 0 doesn't really matter. You have, regardless of how many significant digits you are using, you will still have the problem. Then we comes up with the modified version of the Gaussian elimination, which is the partial pivoting, which will be a remedy for both of these problems, as I will see, and this is what we will discuss. I will just go through it very fast, so we have some few minutes, and then we'll talk about the examples in next class. So what is this partial pivoting technique? What we should do? And here you reach to the kth step. You apply it during the forward elimination, okay? And you are in the kth step. So this is your matrix. So this is your matrix, and here you are in the k step. Here you are in this step. You are reach here. So you check the kth element until the end of that column. Okay. If this k element is the highest among all of them, you don't need to do anything. If you find another row has a higher number in that column, you swap these two rows, and then you move and you do it the same way, or you proceed as regular as you do in forward elimination. So for example, here you finished the first column and everything is 0, and now you want to move to the second column. Okay, so now I don't care about the first element because this line is done. This is done for me. Okay, so now this is the 1, 2, 3, 4 equations or 4 lines I need to deal with. So I come here to the kth element in the diagonal here, because this is always will be the starting point, and I will compare it to all the elements, and I will compare the absolute value. I will compare the -7 to 4 to 9 and to -17. Obviously, the largest number is this. So what I do, I will swap this row here and this row there. This is what I will do. So now this is my matrix. Okay. Now this does not affect my answer at all. I just removed one equation from the bottom to the top, and I take that equation at the bottom. So I'm just changing the order of equations. I didn't do anything. But we do this after each step. Now once you are done with this, you come to this element and you check here. But not now. When you are done with the elimination, you come to this element and you check. Is this number is the highest, or there is another number is the highest? So you keep doing this. You keep on checking all the elements. And actually, as a matter of fact, you start from the beginning here. But this is I show it to you after I finish the first step. But for instance, if I have something like this, if I have these are my matrix. Let's say 6, 2, 3, 4. I just have some arbitrary numbers: -10, 1, 4, 9, 0, 0, 2, 3, 4, 6, and 3, 4, 1, 8, 9. So if this is my matrix, so now I will start here. So I have to look to all the elements. Obviously, this is the absolute value of this row is highest. So I will swap these two rows together, and then I will start the process. And I finish. After I finish, I will move here. Always we move to the diagonal elements, and then I will check. Done. After I finish this, the substitution, I go this way, etc.